All right. All right, let's spend about 15, 30 minutes talking about different modeling methods in HMS and then go over our suggestions. And we can modify these suggestions too. If you all have any wins for different methods in your area, then please speak up and let's talk about those too. All right, modeling methods, let's go. So the objective of this talk is learn about suggested HMS methods for real-time modeling. We'll talk about Canopy methods, loss methods, transform, baseflow, and routing methods, and then spend a second on snow methods. We're not going to talk about surface methods. For most watersheds, you don't need to turn on the surface option. I believe only those in the upper Midwest use surface grids. But if you want to learn more about it, just contact me separately and we'll talk in detail. All right, Canopy. There are 3 Canopy methods in HMS: dynamic, gridded, and simple Canopy. For most applications, maybe 100% of them, we could go with all of them. The simple Canopy method is going to be fantastic. The way that I would suggest that you parameterize it is shown on the left side of the screen here. You can do a max storage of 0 inches. So effectively what you're saying is the canopy doesn't store water, but you need a canopy method turned on so that the canopy is what's responsible for removing water from the soil layer. Okay, so if you're using deficit and constant loss, which we suggest that you use, you have to have a canopy method selected, and you can configure it just like this, which takes very little input. And for most of your calibrations, or maybe all of them, you'll never have to really touch the canopy method. Okay, it's simple, but it provides valuable information for your losses. Okay. One thing that I noticed down here, so the uptake method, what this really means is the method that the vegetation pulls moisture from the soil layer. If you're using deficit and constant, then you want to choose the simple method. What's a little bit funky is that whenever you select the canopy method, so if I select the simple canopy method, by default, for some reason, the uptake method is set to none. So you want to make sure that, take a look at your models today, make sure that the uptake method is set to simple. And Jody, if you're on, this is one of the suggestions I had for you. I noticed in the ACF model that we were looking at the other day, there was a warning method that the uptake method hasn't been selected. And you'll make that warning message go away if you just choose simple. Okay. All right. And then the figure on the right side, this just shows you precipitation for a subbasin in the upper viewport, and then moisture deficit here, and then the saturated fraction here. The reason why this is important, this is how you know that the canopy method is properly configured. If you see during those periods of no precipitation, like January 5th, 6th, and 7th here, or 5th and 6th, you'll notice that the moisture deficit is growing. So that's your clue, or your visual clue here, that moisture deficit is being removed from the soil from the canopy model. Okay, so super simple, but very valuable. Any questions on the canopy method and the suggestions here? Oh, there we go. Recommendation, simple canopy. All right, let's talk about the loss methods. I believe initially in the SWMS National Implementation Program process, the NIPP, the initial and constant loss method was used in a lot of watersheds. Initial and constant is fantastic, but the only thing that you have to watch out for that is it is not set up for continuous simulation. So the canopy method doesn't talk to this loss method, initial and constant. There is no idea of moisture deficit growing between periods of no rainfall. Okay, so our suggestion is, if you have initial and constant in your model, migrate to deficit and constant. You can use the same parameters. You can use the same constant loss rate and percent impervious area. The only new parameter that you have to set is the maximum deficit. And that maximum deficit, you can set it to 4 inches for all subbasins and that's going to be good enough for most cases. So it's really easy to it's really easy to configure deficit and constant if you already have initial and constant loss set up in your model. There's other infiltration methods. I don't suggest you use these methods unless you have a really good reason. I'll say 4 really is there. Green and amped and layered green and amped, those are good. I really think those are specific for steady models. There's a lot of tuning knobs in those, and I don't think you have enough time during a forecast optimization to dive into and change multiple parameters that impact infiltration. Okay. Exponential is the same way. There's like 5 or 6 parameters. Smith-Parlange, I've not seen that used at all, really. Curve number, the reason why we don't recommend the curve number for flood forecasting is it is an event model. So there is no idea of moisture deficit in a continuous sense. So stay away from this one for flood forecasting. I have seen a few watersheds use soil moisture accounting for their forecasting model. This one is interesting. There's tons of parameters in soil moisture accounting. It does do really well term simulations. So if you're looking at a 2, 4, 6 month forecast into the future and soil moisture is a big driver of the runoff response, then this is a good routing or a good loss method to use. It's going to take a considerable amount of time to get an idea for the reasonable parameters to use. Okay, so you're going to have to invest, let me just throw out 2 weeks maybe in a couple of calibration events to get a really good idea of model parameters if you're using soil moisture accounting. So recommended methods here, deficit and constant. That's the one I would really recommend that you gravitate to if this is not already set up in your project. Any questions or comments on the loss models? Does anybody?
Matt.
Yeah.
Yeah, so, and maybe this is something you're going to cover here coming up soon, but are there any particular settings on the Canopy method that we have to set to get the ET right?
Oh yeah, so the ET rate, yeah, we'll cover that in just a minute, Ken. Yep.
Okay, that's what I wanted to.
I have a question for the Canopy as well. So our Canopy used the one that was suggested, but looks like all the max storage is set to 0.1. Is it worth changing that to 0? Like, is that having an impact?
It won't have an impact. The reason why I'm suggesting setting it to 0 is, in your loss model, deficit and constant, you have that initial deficit, right? And you can use that initial deficit to accumulate canopy, surface, and soil, right? So you don't have to have multiple initial deficits in the canopy method and in the loss model too. So that's why I suggest keeping it simple with 1 in the loss model. All right, does anybody use? Yeah.
A little bit further up on loss methods that we've been working in our basin, installing some soil moisture gauges. So we've been doing some correlation to try to do between our initial and loss parameters, but thinking about the soil accounting, see if that would be a way to try to incorporate that data and see how that compares. Just kind of wondering what you think, how to best implement some of that data now that we're pulling it in.
Yeah. Oh, I love that. So that there's soil moisture gauges going into the watershed, and wait, where's that? Oh, let's go back up. There. All right. So you have soil moisture gauges. They don't measure how HMS keeps track of moisture deficit, right? So HMS has a moisture deficit state variable. Those soil moisture gauges, they report fraction. Is it saturated fraction or?
Yeah.
Yeah. So what you'll have to do is relate, and that's what you can kind of see in this figure here. This shows you for this subbasin, here's the moisture deficit, and saturated fraction it's at 1 if there is no deficit, and then it grows as the deficit gets larger and larger. What you can do is do some kind of correlation analysis between what's measured in the field, and if you had a long-term continuous simulation in HMS and the times overlapped, right? You would just go to your HMS model and pick off, this is what HMS estimated or computed for that time that soil moisture gauge recorded something, right? And so you have that correlation done, and then in the future, whenever you're doing a flood forecast, you would look at, well, this is the soil moisture gauge now, and use that analysis to help you and help inform you what a great initial deficit is going to be.
Okay.
And you could even write probably a script too to automatically run the analysis, and then I don't know how it would work but if it could run that analysis and push those initial deficit values into the HMS parameter set.
Sure.
That'd be really cool.
Okay. Yeah. Thanks.
Yeah. Yep. Does anybody use a loss method that's not deficit and constant or initial and constant? Well, if you do, it's not the end of the world. It's okay. Let's see here, Paul. Why wet versus wet and dry for evapotranspiration?
For simple canopy.
Oh yeah.
In the drop down.
Yeah, it took me a second. I was like, what?
Sorry.
No. All right. Yeah, there's a couple of options here for evapotranspiration in the Canopy method. By default, evapotranspiration is only being computed when there is no precipitation, right? It makes sense when there's no rainfall on the surface for evapotranspiration to happen. So that's the default. You can switch it to wet and dry periods, so at every time step. And the reason why you would do it at every time step is for those models that have, a longer time step, maybe 6 hours or 12 hours. For those models with longer time steps, you usually have a little bit of precipitation throughout the day, or a lot of periods. And if you had just a little bit of precipitation and it's set to the only dry periods option here, then effectively you get no evapotranspiration computed from the soil. So it's really only designed that wet and dry periods for longer time step models, probably 6 hours to 24 hours for the time step, and also for your snow models too. I've noticed for the snow models, right, so you have your snow melt happens during the day, and you have every time step throughout the day has a little bit of a melt. What happens is if you have that little bit of melt during the day, then you're not getting any evaporation or evapotranspiration computed if this evapotranspiration method is set to only dry periods. Okay, so for those snow models out there and you're doing a long-term simulation with snow melt, I would also suggest that you switch it over to wet and dry periods for evapotranspiration. Yeah, thanks for bringing that up, Paul.
Yeah, I think I used wet and dry, and I don't remember why, but I was seeing a difference, and it seemed like it was helping some. I don't necessarily meet those examples, but maybe I shouldn't be.
No, you can, totally can. It does make sense. Like for this figure here, we have all that rainfall on the 8th and 9th and 10th and 11th. So effectively, if you notice, there's very little happening here with the evapotranspiration. So if you wanted to increase it, maybe it helps with the calibration, then wet and dry periods would be better. Yeah, those are just my general recommendations. Yeah.
Sure, thank you.
Talk about transform methods. My guess is that all of your models use the Maud-Clark or the Clark transform model, and that is fantastic. There are other options. I really don't recommend the other options for flood forecasting unless you have a really good reason, right? So if you have unit hydrograph, user-specified unit hydrographs already defined for subbasins. I know the National Weather Service uses the user-specified unit hydrographs, so they've computed unit hydrographs for their watersheds And so if your watershed boundaries exactly line up with the National Weather Service and you want to reuse their unit hydrographs, then I'd say go for it. That's fantastic. The S-graph is just like the user-specified unit hydrograph. Kinematic wave, this is only a unit, or it's only a transform method that you use in really steep watersheds. 2D diffusion wave, you don't have enough time in the day to use that one if you need to turn out a calibration within 30 minutes or an hour. Snyder, I think folks from the Southwest Division districts use the Snyder method. That's great if there's regression equations that help estimate the Snyder parameters. That's cool. The one thing to notice about the Snyder method is even if you use that method, the Clark unit hydrograph method's being used behind the scenes. So there's a couple of equations that define the Snyder unit hydrograph, and then HMS, whenever you run a simulation, it fits a Clark unit hydrograph to the Snyder unit hydrograph, and that's what it uses for the simulation. A couple of notes here that I want to bring up about the Clark and the mod Clark method. What I find very valuable about the Clark method is there's a new option to vary the Clark parameters based on precipitation intensity. And so why that's important is the reason people have to calibrate the unit hydrograph from event to event to event is because that unit hydrograph or the unit hydrograph parameters are event specific, right? Those parameters describe how fast the water moves off the watershed. If you have a dry watershed and a small amount of rainfall versus a saturated watershed with a high intensity rainfall, you know the water is going to move off the watershed quicker for case number 2. And so for case number 2, your time of concentration and your storage coefficient would be different than case number 1. And you'd have to manually go through the model and make those changes if you wanted to accurately capture the runoff response. What you can use with the variable Clark option is you create basically a rating curve or a lookup function that says for this precipitation intensity, this is my time of concentration. For this precipitation intensity, this is my time of concentration. You don't have to go wild and crazy and have a curve with tons of points on it. You could have a very simple relationship with three points: precipitation intensity of 0.25 inches, 0.5 inches, and 1.5 inches, right, to cover a range of conditions in the watershed. So I'd really suggest taking a look at the variable Clark method. Before version, it's in the notes right here, so before version 4.13 of HMS, with mod Clark, you could not use this variable option, but with 4.13 and after, this does become available. So this is just something to consider in the future if you want to create those relationships, which I think those relationships are going to be regional in the future. Hopefully there'll be some guidance on how to come up with those relationships, but it could be a game changer where once you have this variable Clark option or variable mod Clark option set up, you never have to change those parameters in the future. They're available based on those lookup functions. Let's see, yeah. Recommendations, Clark or mod Clark method. Any questions about Clark or mod Clark? All right, saving it for Baseflow. My guess is all the models that you have are using the mod Clark method, except for maybe some Fort Worth or Tulsa watersheds, which is fine. They might be using
even Fort Worth, we switched over to Clark for forecast. I think there's still some multi-study models that have Snyder's, but
okay.
Yeah.
Oh boy, so here's, I guess, maybe where some of the questions will come in. There's a few Baseflow methods in HMS. I'm pretty sure that when the models for the National Implementation Program were set up, they were set up using the recession Baseflow method, which is, I think it's a fantastic method. If your model has bounded recession in it, my suggestion is don't even go home from the office today without changing it from bounded recession to recession or linear reservoir. Don't use this method. It was implemented originally 20 years ago, or even more than that probably, specifically for water management to use. It wasn't, I don't think it ever worked correctly. So if you have bounded recession in your model, take it out. The two methods that I really recommend, recession or linear reservoir base flow. The reason why I like linear reservoir base flow is it conserves mass. And it's really designed to work with those continuous simulation methods for loss models. Okay, so let's talk about the deficit and constant model. When you begin the simulation, you have an initial deficit. And let's go back up to that one figure that we had. Right here. All right, so we have deficit. When we began this simulation, the deficit is 0. So we started the simulation assuming saturated conditions. Okay, and so when we get to periods where there is no deficit and it's raining, so right here on the 8th, January 8th, we have all this precipitation, the soil is saturated, there's no deficit, then the model is using that constant loss rate. And based on the constant loss rate, there's going to be infiltration into the soil. And then the way that the base flow method is linked to this loss model is whatever is infiltrated based on that constant loss rate and the soil is saturated, then that infiltrated water percolates to what we call the base flow layer, and it's divided between groundwater 1, 2, or 3. And you get to choose. If you want 3 layers in linear reservoir, then you can have 3 layers. If you want just 1 layer, you can choose just 1 layer. And then you can define, well, based on how much infiltrates into the soil, what's the percentage of water that infiltrates that goes to those different base flow layers. Okay? And I think Paul tomorrow has some really good graphics that describe this in detail. I'm just giving a quick overview today. But the reason why I like it, again, is it's all mass conserving, right? Water that infiltrates into the soil, it goes to the groundwater layers, and then it can run off back onto the land surface. With your recession base flow method, there is no conservation of mass. And let's see here. There we go. I have a nice figure here that describes that. Here we go. Here's a simulation that uses the recession base flow method. And you notice here on the hydrograph, which is the dashed line. Let me just turn some of these off. Let's go hide. There we go. This dashed line represents the runoff from a subbasin. And you notice with recession, once you get to a certain point on the receding limb of the hydrograph, then this recession curve just turns on, right? You have very little control over the volume. Like there is no control on volume here. And visually, when I look at this figure right here, it looks like more volume is being generated in the runoff than actual precipitation, because there is a ton of volume under this recession curve right here. And you can just verify that if you go to the subbasin upstream and choose your summary table. Yeah, just like I thought. So the discharge volume is 15 inches. The precipitation volume is 10.5. Okay, so that's a big red flag for me. Your runoff volume shouldn't exceed your precipitation volume. So what you'd have to do during the forecast is you'd have to come to the base flow and then change this recession constant. So this recession constant, if I had dropped it to 0.5 and reran the simulation, it receded a little bit more. No, it did not. That's what I get for real-time demonstrations. Well, I'll look into that later. It's not working like I thought it would. Okay. Well, what we should have seen is the discharge volume. Oh, you know why it's not working? Yeah, let's talk about this. This is really important. So if you saw me get flustered and fumble around here. This is why it happens. And this happens to all of us periodically. You start making changes to your basin model and the results don't update. Like, what's going on? HMS is broken. You know, it's not broken. We have a forecast selected here. And if we go to the compute menu and then open the parameter tables, the zonal editors for recession, and then let's take a look at this. So you notice in this zonal editor, there's an override for that subbasin, or for the, there we go, for Baileysville local. So there's those overrides. And what we talked about yesterday is anything that's in this zonal editor and the element override table at the bottom wins all the time. So you could be changing your parameters in the base model, but whatever is in this table is what's going to win all the time. So let's take a look again. Let's get it configured here. Come on. There we go. So what you have to do is you have to come to this table and you would change that ratio to peak or this recession constant. So 0.99, that is a really high recession constant. It should be something much smaller. So apply. And let's open up that summary table one more. Oh, it's right here. There we go. Oops. My gosh. Okay. There we go. Now our discharge volume is much smaller than the precipitation volume. Yay, the world has righted itself. Things are working. All right. All right, Paul, what you have here with recession, don't use a threshold discharge. Yeah. Yeah, that's right. So for recession base flow, there's a couple of options for, let's just go there real quick. Threshold type, ratio to peak, or threshold discharge. What Paul's saying is you want to stay away from this option. Ratio to peak is much more independent of the event that you're simulating. And what ratio to peak means here is right here it's set to 0.5, or sorry, in this table it's set to 0.3. And what that means is when the receding limb of the hydrograph gets to 30% of the peak value, that's when we turn on that recession curve right here. So if I zoom in, let's just zoom in. My guess is, so the 8,000 CFS is the peak flow. So 30% of that is about right there, around 2,000. Whenever you get around 2,000 CFS, that's when we turn on that recession curve. Okay. So that's the recession method. If you use that, you're probably going to have to do a bit of fiddling when you're calibrating the model and modify that recession constant and that ratio to peak. So I'll stop there and see if there's any questions. Oh, yeah, Fatima, that's a really good question. Is it better to turn off the override or manually enter it into the table? So are you referring to, is it better to use this table at the bottom or the zonal table at the top?
When you changed it from 0.9 to 0.3, you use the bottom table, but there's also a little blue check mark on the left. If you turn that off, then you could just use the regular like combined parameter editor without having to worry about like doing an individual subbasin, because we typically do not calibrate subbasins. We just do the computation points.
Yep.
Or is that sometimes that level of detail necessary?
Yeah, thank you for bringing that up. That's a really good topic. This is just my suggestion is if you need to get through a fast calibration, don't get down into this lower table and start making adjustments incrementally down here for subbasins. Use this upper table, which is the zone table, and make those global adjustments, right? So what I can do here, instead of going down here, I'm just going to specify 0.5 for the recession constant globally and click apply. And now all of those subbasins have a recession constant of 0.5. Okay?
Okay.
And so if you're only concerned with the outlet at the bottom of that zone, this is exactly what you want to do. If you really do have the time and you can get into the details, then, and you have observed flow at the you have multiple locations of observed flow throughout the watershed, then you could get down here into this lower table and start modifying parameters per subbasin.
Okay.
All right.
Great, thank you.
Yeah.
Another thing that I've noticed with HMS not reacting is sometimes I have to close HMS and run it in the CAVI, the whole, like all the computation points in CAVI, and then I'll open up the graph and it will have reacted.
Yes, that's right. Well, even if you close the results plot and then reopen it without having to close the forecast, do the results in the plot look right?
No. So what I would still have the forecast open, but I'll just close the standalone HMS and run it, compute through the CAVI button the whole watershed instead of just computing to like one point. And that will have then the HMS graph will react to my changes in the parameters.
Yep. Shoot. So I just got my computer refreshed, and when I open the CAVI, MetView is not loading for me. So I can't show a good example. I can't bring it up to talk through what you're talking about, but I'll describe it. If you're in the CAVI and you've created your forecast and you open up the combined parameter editor. So let's just assume this is my combined parameter editor. In the bottom left, there is the option to run the forecast, right? If you click this button, where my mouse is showing right here, this runs the forecast. It only saves the results within the HMS directory of the forecast. Okay. It doesn't push the results automatically to the forecast DSS file. You have to run the HMS portion of the forecast from the CAVI. You have to right click on HMS in that in the tree on the left side. And once you run it from that, then you'll notice at the very bottom of the message window, it says copying results to forecast DSS file.
Okay. I think the problem was that I was using a combination of graphs maybe. Maybe I was using the graph from the CAVI when you do the drop down, and then I was using the combined parameter editor, which runs in HMS. So that's maybe where the mix-up comes from.
It could be. We have found a bug recently where plots were not updating in 4.12. The HMS team just fixed it yesterday. So if you're still having a problem when you're working with SWMS 3.4.1, let me know, and we'll insert a newer version of HMS and see if that clears up the issue.
Okay. All right. Thank you.
One other thing before I jump to the comments here, I pulled up the deficit and constant loss editor for this watershed, or the zonal editor for this watershed. And you notice here for my north zone, I'm using this adjustment factor. It's asterisk 2. So I'm multiplying by a factor of 2. And the reason why this is a good approach too is you notice for the 4 subbasins in this zone, they had different constant loss rates defined in them in the base portion of the basin model. let's just assume these constant loss rates were based on a calibration event or based on soil information, so they vary from subbasin to subbasin to subbasin, right? So if you just use this multiplication factor in the upper table, it's going to multiply a factor of 2 by all of those original values, and then this is what you get during the forecast, okay? So you can make use of the spatial variability by using this multiplication option. If I came to this editor here and just entered a value of 0.1 and hit apply, and now that value of 0.1 is going to be applied to all of those subbasins. Okay, so you get removed from that spatial variability of that parameter if you do it that way. Both are great options, they're just a little bit different. All right, let's see, let me check Emily's post. Yep. All right, well, hopefully my running into that issue highlighted things that you were seeing. Frustrating. Okay, let's jump into linear reservoir. We've kind of already talked about it. I know we're running short on time. So linear reservoir, that's going to be the method that conserves mass. And I'm just going to rely on Paul tomorrow. He's going to go into some of the details and show you how changes to parameters for the linear reservoir method, how they impact results. Okay, and we can also talk about tomorrow, if you need to make the switch from recession to linear reservoir, I have a really quick way to parameterize that model. So we can make some simplifications and you can get the parameters in there really quick. All right. So yeah, those are the two. I did overwrite what Alex had in there. Alex had just linear reservoir. I'm going to keep recession because I think the recession method is great. If you're familiar with it, you just have to be careful that you're not creating more mass than the precipitation. Okay. Routing methods. I'm guessing your models have a mixture of routing methods, reach routing methods. They probably have modified poles, Muskingum, and Muskingum-Kunj, at least. Maybe even more than those three methods in one watershed. Or lag. Lag is a great option too. One thing that we kind of touched on yesterday that I would definitely suggest is there is the lag and K method in HMS. The lag and K method is just like the Muskingum method. Okay, they're basically the same. The one thing that you have to remember with the lag and K is it's really called the variable lag and K, because you can set up relationships between flow rate and the lag time and flow rate and that K value. Okay, so it's variable lag and K, and I believe the variable lag and K is what the National Weather Service used or still uses as well. So there might be some transferability of parameters from their model to your model if you're interested. Modified poles, definitely, that's probably going to be the method that's used for those reaches where there's a RAS model, and probably at some point somebody created those storage discharge relationships for your model. Muskingum-Kunj, let's jump down to that one. A lot of models have Muskingum-Kunj in them. This is probably the one method in HMS that is the most computationally burdensome. Okay, so if you're noticing long run times, it's probably because of the Muskingum-Kunj method. And we talked about this yesterday. You can save some time if your reaches are less than 10,000 feet. You could probably turn that Muskingum-Kunj off and just use the lag routing or no routing. Or whenever you have some downtime, you could look at changing from Muskingum-Kunj to either Muskingum or the variable lag and K. Okay, if you make that switch, you're going to save a lot of runtime in the future. Here, let me pause there. Any questions so far?
Hey,
Kevin,
Matt?
I think,
Yeah. I was just going to point you to Kevin's question or comment.
Yep, we're going to get down to snow at the very end. For some reason, snow is at the bottom, even though it's at the top in the HMS selection list here. Evapotranspiration, let's touch that real quick. There's a couple of methods. I'm guessing most models use either Hammond or monthly average. The thing about the Hammond method, though, is you have to have temperature for every time step. So if you're bringing in your temperature grids and there's missing temperature values for one grid cell or one time step, then it's going to be a pain to resolve that. MetView does have a nice option in it to, if it encounters a missing grid cell or missing time step, it will create, it'll fill that in for you, and you can choose the temperature value, right? And so if you choose a temperature value of 50 degrees Fahrenheit, that might be a good fill-in value for anything that's missing. So just be careful with that. So with Hammond, you have to have a value for every time step with temperature. Monthly average, that's definitely going to be the easiest one to parameterize. There used to be an old EM out there. I think it was rescinded, but you can still find it. It has monthly lake evaporation values across the country, and you can use those lake evaporation values as quick estimates for evapotranspiration, or I think in most reservoir regulation manuals, they have monthly average evaporation too. And you can use those values to parameterize that monthly average table in HMS for each subbasin. There is a global parameter table for monthly average. So if you don't want to go through the HMS tree and define those relationships for each subbasin, you don't have to. You can open up the global parameter table. And if you can't find it, just reach out and I'll show you how to get that open. All right, let me pause there. Any questions about evapotranspiration?
Do you like specified ET?
Oh yeah, specified ET. You can define a time series of evapotranspiration too. You would just have to be careful for your forecast that you have a model running and a time series available in that forecast period to generate that specified evapotranspiration. So yeah, it's totally a good method. It's just you have to make sure that you have a value for every time step during the simulation window.
Yeah, we use it fairly heavily in Fort Worth, and I got a little demo on that with my talk this afternoon. So
fantastic.
Cool.
Okay. Yeah. All right, then we need another check mark. We need specified ET here. All right, snow methods. This is the last one, and then we'll turn you loose to take a look at your models. There's 3 options for modeling snow in HMS. Temperature index has been around for 20 plus years. There is a hybrid radiation-based and an energy budget-based. For now, I'm just going to recommend you stay away from those. Only look at them when you have some downtime, when you're not actively forecasting. The thing about these 2 methods is they take longer to run, and they take more boundary condition data, more input, right? So if you're running the energy budget, then you're going to have wind speed, solar radiation, humidity, and I think like 2 other things. And it just takes a long time to run. So stay away from those for now. But temperature index, let's see here. What can we say about that? I think Paul will talk about this tomorrow. With temperature index, if you have a solid model, so if there's already been calibration and you're looking at your real-time events, and if it's a rain on snow type of event, then there's really only 2 parameters that you have to change. It's the wet melt rate, right? That's what's triggered during a rain on snow event, and also your px temperature. That's the temperature that differentiates between frozen and liquid precipitation, right? So even though there's tons of parameters with temperature index, if you're simulating a rain on snow event, then you just have to worry about those 2. If you're looking at a long-term forecast, months into the future, then your dry melt rate or your melt rate ATI function is important, and probably the base temperature. Right, so you can really reduce the number of parameters that you adjust based on the type of forecast you're doing. Kevin, what are you looking for here is a snow parameter forecast table?
Just like similar to the other parameter tables. So I find that being able to adjust like PX and like just the same parameter tables that we see when we're looking at like Baseflow or any of the other things when we're
Yeah, those should be available. Let's just take a look here. So with the trick with that is for the forecast alternative. There's a snow configuration here. You have to make sure that you have a zone configuration chosen there. And once you do, and you have a snow method, then you can open up the snow zonal editor, and just like the other methods.
Well, looks like I just wasn't clicking a button.
Yep. It's pretty new too. I think this came out in 4.12 or 4.11. Yeah. Maybe 4.10. Time is bleeding into each other for me.
Oh.
Kevin, one thing that we've noticed in our basins is that snow, we have to use different zones to calibrate. We need like the high elevation and the low elevation, basically. So if you're setting that up, I would recommend that.
Yeah, that's a really good point, Leah. Your zone configuration for snow is going to look different than the other configurations because snow parameters are more regional, I think, right? They're a bit different. The zone configuration, I think Simeon will talk about this more in detail later today, but zone configuration for your loss parameters is probably going to follow your calibration points or similar to your calibration points. For snow, I'm guessing you could have fewer zones.
So
yeah.
I guess that brings up another question. We were talking yesterday about like the merging of different subbasins. Is the snow parameters like the PX and PT, whatever, base snowpack building parameters, is that spatially distributed, or if I merge my subbasins, is it going to use that same value for the entire subbasin?
Yeah, it's variable by subbasin. So if let's go back to this one example here.
I was thinking the same thing, kind of along the like, okay, do we merge or do we not merge? Would be a reason to not merge is like if we're using snowtail sites for like calibration, or yeah, would the snow parameter and the importance of snow in our basin influence if we wanted to merge or not?
It shouldn't, right? As long as you have, for each of the subbasins, well, okay, now I see what you're saying. Let me back up just a little bit. So in this model, and you could just assume that we're looking at snow parameters. So let's just assume your constant loss rate is your PX temperature. And for each of the subbasins, that PX temperature is different. You can use the zonal overrides, just like what we talked about a few minutes ago, and multiply those PX temperatures by a factor. Or you could just set all of those PX temperatures to the same value.
Okay, can I show you my screen really fast?
Oh yeah.
I don't know that I'm communicating the question very well.
Oh, please show.
Okay. So this is the Rogue Basin, right? So what I'm mostly talking about, or what my question is referring to, is like a headwater. So like I was wanting to combine these two. I was thinking about merging these two. However, the snowpack is dramatically different in this basin versus this basin, and just the way that the mountains wrap around like this. And so what I'm wondering is, am I going to be able to actually match the snow melt very well if I merge these two, if these sometimes have different PX levels just between the two subbasins?
Yeah, you can. This is like hydrology. This is the classic question for hydrology: is how much averaging can you do and still get a reasonable result? The calculations here are still being performed on the grid cells, right? So you have a 2
Okay.
kilometer grid, and you're getting temperature, you're getting precipitation and snow buildup on those individual grid cells. A slightly different PX though, if you use one PX for both subbasins versus a slightly different PX, like you're not thinking the PX is 34 in the lower subbasin and 40 in the upper, right? It's not that drastically different.
It's not. Yeah, it's not that drastically different. No.
No, so it's if the difference between the two subbasins is slight, like 36 versus 35, and then if you combine them, you're using 35.5, it's a wash. You're not going to see that big of a difference at the outlet of the subbasin.
Okay, so then you would probably just merge them at that point. Is that?
That's what I would suggest. But just for fun, before you move forward in a final direction, you can have two separate basin models, right? And one's merged and one's not merged, and run the same simulation. And you can start diving into the results and see if they're different in a bad way or just different.
When I start doing all the merging, I'm just duplicating this one and I'm creating a new one off of that duplicate.
Perfect.
But
yeah.
Okay, thank you.
Yep.
So I guess my question is more like, okay, merging two subbasins, depending on them, like probably doesn't make a difference. But I know we've been talking about like merging like all the points above or all the basins above a computation point, for example, because they're in the same zone. But because we're doing the way we're doing, or we plan on doing it, is to have like a high elevation zone and like a low elevation zone for our snow parameters. So then we wouldn't necessarily want to merge by computation point. We would want to maybe do like a little bit smaller clumps for the merges.
The problem with that
sense?
is you can't merge the basins unless they have a common computation point, like if they're all pointing to the same junction. So like with the way mine's set up right now, I'm gonna have to change that upper basin to be pointing to the same computation point as the lower basin, or else it won't let me merge them. So they have to share like a common point that their subbasins are pointing at.
Yeah, but what Leah's saying though is if she just wanted for snow two zones, one is upper for all the upper subbasins in the watershed, the entire watershed, and one for lower, then if she started merging those together, like what you just showed, Kevin, then she wouldn't be able to go that route.
Yeah, probably not.
Because we've been thinking about merging, and like I've been resistant because I was trying to figure out the downfall, but I think this is our downfall. I think this would be a reason why we wouldn't merge and just stick with our zones. But yeah.
That's fair. That's really fair. I like that.
Because like Matt and Kevin, you guys have both been like, you need to merge. But I think this has helped me decide that we shouldn't. So, but it sounds like you might agree with that. Like in general.
I agree in general, but before you make the final decision, I'd say do a little investigation and try it out for a small portion of the watershed and see if there's savings in runtime and calibration effort versus the quality of the results.
Yeah. Okay. Thank you.
Yeah. One last thing I have on snow. I've seen some watersheds where they're using METView to process the calculated no risk SWE data, and they've linked it into their HMS model, and they're comparing SWE results at all subbasins in the watershed. It sounds great. You don't have enough time for that, and you can spend a ton of time on calibrating SWE, but then your flow looks like trash. So my recommendation is choose a few subbasins where you want to compare the computed SWE to the observed, or air quote observed SWE, don't try to link that up to all subbasins in your HMS basin model. All right, so if you want to throw tomatoes, great, I'll be ready for it, but that's my recommendation as of this second.
I have another question. When you're calibrating snow, you just look at the graphs for like the basins that you pick out and just be like, this is good enough, or?
Yes. Yep, that's exactly
it. Okay.
Yeah. Yep.
I was just curious if there were other ideas, right? Because like we also care about like just okay, how accurate is our peak snow, like the snowpack on the last day.
Right. Right.
So
and
yeah, I was just curious.
And you got to be careful with that. I think Fatima pointed to this too, is what you have from no risk or other data sources, it's a modeled output, or it's a point value. It's not a watershed average. And so the quality of those observed SWE estimates are not that great. So trying to force or judge your model performance to those is a little tricky. Yeah, Emily.
Yeah, so I'll just kind of jump in on that. So what we've done in St. Paul is Matt has told us not to link our no risk SWE observed data to every single subbasin, because sometimes we do have, some of our models do have like 50 subbasins, and that's a ridiculous amount of gauges, and the data is sometimes garbage too. But what we have done is we have selected a handful of basins that we do monitor, and sometimes that can vary from year to year too, just depending on how each region gets hit that year, I guess. So what we've kind of started to do is at the peak SWE, we kind of look, we run through METView with the SNODAS and look at the basin average SWE across the entire watershed, the output from METView there. And there's usually like 2 or 3 trends where like, oh, okay, up in this region, it's tracking high. And then over here, it's doing something slightly different. So then we pick representative basins from each of those like kind of trends that we're tracking, and then focus on calibrating those instances and then move forward. And that's kind of helped simplify things. So generally, like if we do kind of just throw it all up through METView initially and identify like, okay, there's a couple different things happening here, it helps identify which basins to look at. And then Matt's absolutely right about don't trust that data if you're using the SNODAS all the way through, because it is really frustrating if you get a really good snow calibration going and then you look at your flow and it's absolutely impossible because the SWE data was off. So make sure that you're comparing it to any observed flows periodically before you go too far down the SWE rabbit hole too. So anyway, that's just our 2 cents that we've kind of been learning about in St. Paul that hopefully might help others.
Awesome. Thanks, Emily. All right. Well, I said 15 to 30 minutes, and I think I lied to you. I think we had some good conversations so far. So what we want to do next is I'll turn you loose. I guess I'll try to figure out how to push you to the breakout rooms. And then you have 50 minutes to take a look at your models, to make a plan for any adjustments that you want to make to the methods that are in those models. And then Emily, myself, Paul, and Simeon are available, and we'll jump into the rooms and see if you have any questions, or if you come out to the main lobby and just ask us, that's fine too. All right.
We thank you very much for your attention through this presentation. If you have any additional questions, would like help, or are seeking additional training, please feel free to check out the links on the screen that are also linked below in the description. If you'd like to stay up to date in whenever more of these videos become available, please go ahead and like and subscribe, and you'll get notifications anytime more presentations or video walkthroughs are posted to this water management channel. Thank you so much and have a wonderful day.